So today we're going to talk about sea level and a changing climate. So the literal rise and fall of our oceans over time. Now we've talked about this already, the fact that temperature and CO2 positively correlate such that when one is high, the other one's going to be high. Um, and if we look at just a difference of 100 parts per million in CO2, that can cause an ice age. So this is the difference between being ice-free in North America, for the most part anyways, and continental-sized glaciers, Saco being under 2 miles of ice. So just 100 parts per million. Now we have to ask the question, what happens when we go way above? So we are currently here. Okay, over the past 800,000 years, the Pleistocene, we've seen the cycling of these ice ages happen due to changes in the Earth-Sun geometry and carbon dioxide. Now, what happens when we're at 417.64 parts per million? Now, we know that big ice has melted before. You can see I outlined Maine right here, but this was the old Laurentide ice sheet. The Greenland was kind of how it is right there. But this covered most of North America here, but also coalesced with the Cordilleran ice sheet over here. At LGM, so at the last glacial maximum, it was about this size. When this thing melted, sea level rose almost 400 feet. That is enormous. And it makes sense that if all of a sudden, okay, sea level rose this 400 feet, about 120 meters with the melting of that, if we think in reverse now, when H2O gets locked up in glaciers, so to make that giant glacier, it's going to lower sea level. So if we look at the sea level over the Quaternary here, at the last glacial maximum, it was really low because all that water was locked up into ice. So glacial periods, it's low. Interglacial, like we're at now, and this one right here, you've got high sea level because the water's returned to the oceans through melting. What this is called a eustatic sea level curve. And what these do is these record global sea level. So this is global sea level at the last glacial maximum. It's going to be really low here. And then once you start returning that water back to the ocean from the glaciers, from the snow, it's going to rise back up all the way up to present sea level. But we also have things like here in Maine, what's called a relative sea level curve. So these take isostasy. So that's how the crust floats in the mantle. And it takes that into account. Okay, so this is the depression of the Earth's crust into the asthenosphere by glacier loading. So when the glacier first retreated from Maine, sea level was actually high. It came way, way inland. And then what happened is, because the crust was pressed down, it then rebounded back up. So sea level was actually really low. And then from there, we could see the changes in eustatic sea level represented onto the landscape. So as a result, what happened is this whole area of Maine actually became an inland ocean. This is what's called marine limit, right when the glacier started melting away. And note that population density matches pretty closely to this area that used to be underwater. Now looking at the more recent records, so the ones of contemporary sea level change, we see that temperatures have risen since the Industrial Revolution. Okay, they've increased in general. We've had some blips in there, but for the most part, they've increased. And we sometimes forget about taking the ocean into account and the fact that the ocean absorbs heat. Water is an excellent substance at absorbing heat. It's got and holding it as well. So it's got a high specific heat. So we constantly think about the land and about the air, but we don't take the oceans always into account, these sea surface temperatures here. And the oceans are absorbing so much heat. And if it holds on to that heat for a longer time, even if we fix things, we still are going to have to deal with the fact that this is a huge thermal mass that's holding a bunch of thermal energy. So like in this particular graph, you can see all the global oceans, but broken up by the North Pacific, Tropical Pacific, Indian, Atlantic Oceans, just how their heat content has changed over time. So when thinking about sea level rise, we've got to take two things into account. One, both melt, and two, density. So when glaciers melt, they return water back to the oceans. Okay, that's this blue line right here. So that's just added water here. So it makes sense. Okay, like we talked about the Earth's axis changing due to the melting of glaciers. It returns it and it rises sea level. But water also expands when it's heated. And I've got a little asterisk here for a reason, but this thermal expansion of water needs to be taken into account as well to come up with our global sea level rise. Now, what the asterisk deals with is the fact that water is its most dense at 4 degrees Celsius. It's kind of a weird substance like that. We talked about this earlier in the year. So technically, I can't say that it always decreases in density as it warms up. So if it was between here and here, it wouldn't. But for the most part, our oceans, most sea surface temperatures are already above that. So when you do heat them up, you're going to see them get less dense. And if they get less dense, we know that density is equal to mass divided by volume. So if they get less dense and the mass stays the same, that just means that your volume's increasing and you're dividing by a greater amount. So if you've ever been swimming before and stuck your feet down and then went, whoa, all of a sudden there's a really cold spot, that's hitting what's called the thermocline. And we see that the densest water is the water that's going to be that around 4 degrees Celsius. That is all going to sink down to the bottom. That's why mostly the warmer waters are up towards the top. So putting this all together, we see that sea level rise has been about 10 centimeters since the early 90s. So going here from the early 90s all the way up today, a pretty consistent trend in what's happening with about 3 millimeters per year. Note that those are the smallest little markings that we've got like on a ruler. And if we add enough melting, so if we melt Greenland, we melt Antarctica, places like that, we could disrupt the transfer of heat throughout the globe and the redistribution of heat to the deep water. This is our global climate engine here. This thermohaline circulation operates on vertical currents that move heat around with the water and keep our planet warmer at these poles. So this is, if you've ever heard of somebody talking about triggering an ice age based off from too much warming, this is kind of that possibility. And then we would see places like Norway and Svalbard and Great Britain getting much, much colder because the Gulf Stream is actually part of this. I said colder, right? Yeah. Likewise, as we increase emissions, we also see that the oceans uptake carbon dioxide as well, because more and more of it diffuses from the atmosphere into the oceans itself. This can have effects on things like sea life, because the more atmospheric carbon dioxide there is, the more dissolved carbon dioxide we've got. We're literally carbonating the oceans here, and we create carbonic acid. That carbonic acid then can lead to things like deformed shells and making it much harder on the physiology of animals that produce calcium carbonate. So accordingly, if you look at this curve, as CO2 increases, this is the Keeling curve throughout the 20th century here, we see that the amount of CO2 in the seawater increases, and accordingly the pH drops down. So in a warming planet, where does this all go? There is the potential for over 200 feet. We're looking at 210 feet of sea level rise if we melt both Greenland and Antarctica. Yikes. That means Saco's underwater. Saco is just at about 70 feet elevation. And if we look at the way that the projections are going, we see how world population is trending. We also see how our carbon dioxide, methane, and nitrous oxides are trending as well. We could be in some worrisome situations. So accordingly, we need to think about different pathways for human emission scenarios. So that means we could make laws and regulate CO2 such we could have this lowest pathway and maybe stabilize our parts per million near that 400 mark. Otherwise, we could end up with lower, higher, or even the highest pathways and increasing the amount of carbon dioxide in our atmosphere significantly. As a result, we're going to see different temperature projections, so different possibilities of temperature based on each of those different pathways and what that will mean for global temperature change and, accordingly, for sea level. So the different sea level projections that we have are based on low, intermediate, high, and high and extreme based on those different greenhouse gas pathways. But what do these look like? I'll admit that when I see something in meters, I'm always kind of like, it takes me a minute to kind of think about it and put it into perspective. But if you follow along to the next video, you may have another way to visualize this. Thank you.